now let's start the class for today. So just a quick reminder that something's annoying. Right. Just a quick reminder that we are on week 10, right? So today is November 11, sorry, week 11. So we are on November 11 now. So supposedly we'll go through solutions today, and hopefully we'll finish it today. And if we don't finish solutions, we might take the next part for solutions, then we don't have review. If we finish solutions today, we still won't have exam 2 review. I'm going to change it to another topic called AI chemistry, since it won the Nobel Prize this year. It's going to be a special topic. But more importantly is next week, so the 12th week. Next Monday, November 18th, we're going to have exam 2. So please mark down on your calendar and remind yourself, set the alarm to make sure to get up early and make sure to come to the class on time. It's going to be the same as exam 1. There will be 25 questions. You'll get an answer card that you actually fill in the circles and make sure to fill in the correct questions. And it's going to be from 10:10 to 11:50. It's going to last for 100 minutes. 好，用中文再讲一遍哦，因为这非常重要。下礼拜一是第2次期中考，所以记得在你的行事历上面把它写下来，然后记得那个闹钟要设好哦。那一样是从10点10分到11点50 100分钟。那跟第一次考试一样，会有25题，一样是图卡，然后就 fill in blanks 就好了哦。记得就是，当然如果你不小心迟到了，还是没关系，还是可以来拿考卷哦。但是尽量就是 it's the time that you all need for the exam. 好，这部分有什么问题吗 ？Any questions regarding exam 2? OK， 好，那我们就开始今天的课了吼。那 hopefully 我们 finish。那当然 exam 2就会包括 covalent bondings, liquid solids 跟 solution 吼。So the contents which will appear on exam 2 will be covalent bondings, liquid solids, and solutions. Of course, we just had a pop quiz on liquid and solids, which will be a nice review for you. And of course, the questions on exam 2 will be very similar questions. So maybe you didn't perform well for pop quiz or you forgot to come, that's fine. It's 5.5% of the final grade, which if you miss or you didn't perform well, you can still get the remaining 95%, right? And if you attend all the classes, you're going to get 5% bonus, which will actually add back to the pop quiz if you happen to miss it. But similar questions will definitely occur on exam 2. So please review the pop quiz. Okay. And I don't think I have enough time to actually hand back the exam paper from pop quiz. So you guys can actually go to maybe after class. 那课堂结束之后你发好了 Okay. Because we actually need to finish solutions today. Okay, let me ensure it's still recording. Okay, it is. All right, and here's a summary of the performance of exam pop quiz. So we have totally 54 students. One student actually, I think he dropped out of the school. And 45 actually came. So about 90% attendance rate on that pop quiz. So if you can, and you actually took the quiz, fantastic. If you happen to miss it, that's fine. There will be no makeup, unfortunately. But if you attend all the classes and get all attendance points, you're going to get 5%. And if you happen to miss any of the attendance, that's fine. Just answer questions on class, and I'll add back the attendance. Okay. And the average was 51.60. So of course not very high. But that's okay. I know it's just pop quiz, right? You probably didn't review for it. So make sure review solids and liquids for exam 2. Those are the difficult part. And as you can see, that's a huge standard deviation, right? So probably some people actually already learned about it in high school. Some people actually reviewed it earlier. So that's the reason for the high standard deviation. And there were still people got 100%, right? So and some people actually performed pretty well. So. And the minimum score, the lowest score was 16. And the mode range, which I actually showed plot here, but somehow it didn't show, was from 28 to 40. That means most of you, a lot of you actually got this grade fall within this range. Any questions? 好，有任何问题吗 好，那这个大家就是记得liquid and solid 确实是这个 exam 2比较难的部分，所以尽量多复习这个部分。好 ，Alright. So today, let's hope to finish solutions, topic solutions today, and then we can talk about some new stuff on Wednesday. And if unfortunately we don't finish today, that's okay. We're going to continue on Wednesday. Alright. There are about 1, 2, 3, 4, 5, 6, 7 topics for this chapter, and I don't think we're going to go to solutes. Okay, solution compositions, thermodynamics of solution formations, factor affecting solubilities, the vapor pressure of solutions, going back to vapor pressure again, like we learned last time. Boiling point elevation and freezing point depression, very important concept. Definitely going to show up if you're going to actually go to graduate school. 所以如果你未来是考化学所的话，这个经常性会考。Osmotic pressure, colligative properties of electrolyte solutions. Right? What's going on? Okay. Alright, in a solution, 这里有一个 formal definition of a homogeneous mixture of greater than one component. So two very important criteria here. One is more than one component. So if you just have water, you just have methanol, that's not a solution, that's a liquid, right? And also need to be homogeneous. That means the particles need to be completely mixed in such a way our eyes cannot see the difference. And usually sub nanometer scale. A solute is the substance being dissolved, right? So it's one will be defined as solute, the other one will be defined as a solvent, and the whole thing is called a solution. 溶质、溶剂跟溶液，对，好。The solvent is a dissolving medium. Okay? When liquids are mixed together, the liquid present in a larger amount is called a solvent. Right? So if you're solid and liquid mixed together, then of course solid will be solute, liquid will be solvent, and the whole thing will become solution. If both are liquids, then you're going to compare which one present in the larger amount. And by amount, it's not mass, it's not volume. It's what? It's their mole fraction. Okay? And of course, then we need to define, right? We need ways to define a solution, to describe a solution, and there are many ways. One is called mass percent. We just directly divide the masses, right? Sometimes called the weight percent. It's the mass percent is grams of solid divided by grams of solution. Right, so you weigh the solute before you mix them together, then you weigh the whole thing, multiplied by 100%. Right? This is commonly used by chemical engineers. 在化工里面大家通常喜欢用 mass percent, OK？ 因为大家讨论都是几吨，calculate mole fraction 太麻烦。The second one is called molality. Molality. Notice it's not molarity, it's molality. And the symbol is small m. The number of moles of solutes per kilograms of solvent. So the difference between molarity and molality is your denominator is not liters of solvent, it's kilograms of solvent. Why is this important? Because sometimes it's very hard to get volume. It's very easy for you to put something on the balance and just weigh out the mass. But it's very hard to use a graduated system to get the volume. And of course, for water at 25 degrees Celsius, grams and mils are the same, right? Kilograms and liters are the same. But for uncommon solvents like ethanol, like dichromethane, kilos and liters are different. Okay. So, and then in a lot of calculations, we use molality, not morality. Molarity. All right. And lastly, which makes more chemical sense, is mole fraction. Right. It's really the molecules are interact each other. Right. It doesn't really matter how heavy they are. Right? Sometimes. So mole fraction makes more chemical sense. And later on, when we derive equations, you'll realize mole fraction is used mole fraction. And the symbol is chi by x. The ratio of the number of moles of a given component to the total number, right? Not A to B, it's A to A plus B. So two component solution where Na is more number of A and more number of B and B. Then the mole fraction of A is chi A is Na divided by Na plus Nb. Okay, so two components Na, right? And this is sample the rest of all the components. Okay, so three concepts you need to remember: mass percent, molality, and the mole fraction. All right. So let's think about how we actually think about solubility, right? And one of the very famous example is actually your body. Right? So this is actually all outside of all your cells, right? This is the membrane of your cell. Right, so for a solution to form, polar solvent depose polar solutes, non-polar solvent dissolve non-polar solutes. So for example, one very famous example is this molecule. This is called DDT. Okay, so a very quick question. Bonus question. 所以如果那之前没有点到名哦，这是加分的机会。So if you didn't actually, you miss one of some of the attendances, this is a chance for you to actually get bonus question. Do you guys know what DDT was used for war purpose? 在战争中 DDT 在什么时候使用哦？One of the very famous war that used a lot of DDT. 二战不对。In the other ones, so he said World War II. 有人知道吗？那 DDT, so let's actually read the description, right? The pesticide, so it kills insects, and it also kills plants, right? Because it actually kills the membrane. It's a fat soluble, it retains that concentrated in animal tissues where it causes detrimental effects. Right, so this DDT, because it's nonpolar, so it's going to dissolve in nonpolar, right? And your membrane, of course, is nonpolar, so it's going to dissolve in the membrane and just break it apart because it's so big, right? So it's going to kill animals, kill plants. 那 DDT 在哪里使用呢？第一在越战。那个当时我们知道二战结束之后兴起一个浪潮嘛，就是我们所谓的共产主义浪潮，因为大家打太多仗争了，觉得我穷死了，对不对？那就共产主义就上来。那共产主义在哪里？当然是那时候的苏联跟那时候的美国嘛。那苏联扶持谁？苏联扶持当然那时候中国虽然他们关系不太好，然后朝鲜、北韩，然后还有什么越南。那越南从哪里呢？是北越，南越就是美国嘛，所以胡志明这边是南越是美国，北越是谁？北越就是现在的河内哦，河内 capital。那当然两个就打仗，对，一边是共产主义，一边是资本主义。好，那当初越战很难打，美国打了8年，最后美国8年美国每4年选一次总统，所以选了2任总统。第2任总统被逼着下台，就是够了，不要再打了，对不对？我们为什么要死那么多美国人呢？为什么打不赢？然后最后美国撤军嘛，因为都是丛林，你是丛林你怎么打？你飞机也看不到，对不对？那怎么办？我就丢一大堆 DDT 把丛林全部烧光，对的，让他们这些植物都死光就好了。但是有一个问题啊，就是植物死光了，但是这些动物会去吃这些植物啊，然后人类再去吃这些动物啊。所以后来越战结束之后发生一件很严重的事情，就是越战结束之后，那些怀孕的妇女生出很多大量的畸形儿。为什么？因为 DDT 都溶在他们 baby 里面嘛，你想想妈妈的营养成分大部分都到子宫去，对不对？所以啊，这是一个人为的非常不幸的事情哦，但没办法发生就发生了 ，OK。所以这个也是另外一个告诉你化学很重要，就是任何脂溶性的东西哦，对人体来说是非常非常毒。为什么？因为它卡在你的细胞膜上面哦，造成你基因突变啊，造成你得癌症哦 ，etc. Alright, just quick translation in English, right? So it was used in Vietnam War, and why? Because there was a conflict between Northern Vietnam and Southern Vietnam, right? And Northern Vietnam was supported by the Communist Party, and Southern Vietnam was supported by the capitalistic party from the United States. And of course, US lost the Vietnam War after 8 years, right? Why? Because there were a lot of jungles, right? So basically, the soldiers were hidden in jungles. So what the US did was spread a bunch of DDT, try to kill all the plants, and of course, it succeeded. But remember, animals eat plants, and humans eat animals, right? So all these DDTs finally got into humans and created a lot of mutations, right? Okay. 好，这是非常重要的课程哦，就是包括之前讲到的 Linus Pauling 化学导致人类现在这么健康，相对的有些时候也是很残忍的哦。Alright, anything. And another example, of course, is your vitamins, right? Vitamins can be separated into 2 categories. One is water soluble, one is fat soluble. 水溶性跟脂溶性哦。Alright, and so really, other vitamins are very important to determine the correct dosage. Water-soluble vitamins like vitamin B complexes, right? A bunch of B's and vitamin C's. While water-soluble, fat-soluble vitamins, vitamin A, vitamin D, vitamin E, vitamin K's. Right? So you can see that vitamin A, all the ones in the red, vitamin D, vitamin E, and vitamin K. And if you already learned about intermolecular interactions, right? So if you just look at the structure, you can quickly understand why. Because these are basically aliphatic, right? A lot of CH. There's only one H here, a lot of CH, one OH here, a lot of CH carbonyl here, a lot of CH, right? So this only one hydrogen bond, and the rest is not water soluble. Only one hydrogen bond, rest is not water soluble. 2 polar bonds, right? Polar interactions, and the rest is not soluble. Now, of course, this huge structure is an OH group. Right, so you can see that if you have a lot of OH, it's going to be water soluble. If you don't have a lot of OH, it's not going to be water soluble. And if you take a look at those water soluble ones, vitamin B1, B2, B3, B5, B6, B7, B9, B12, those are water soluble. Why? OH, NH, and OH, a bunch of OH, a bunch of etc. Right? And vitamin C, of course, is what you eat a lot and a lot of OH. So just by judging at the structure, you can already know which ones are going to be water soluble, which ones are not going to be water soluble. Right? And another very example is the insolubility of barium sulfate means it can be safely used to improve X-ray image of gastrointestinal tract, even though barium 2+ ion are toxic. Right? So solubility products. I don't think we are learning solubility products in this class. 好，那快速用中文讲一下啊。Vitamin A、D、K 是很特别的。为什么呢？因为虽然我们叫它维生素，然后并且是脂溶性，但是 Vitamin A 跟 Vitamin D 正确来说，它们其实是荷尔蒙。它其实因为它是脂溶的，所以它可以直接溶进你的细胞核里面去。那在干嘛？它溶进细胞核中，你的 DNA 就在里面嘛，所以它可以启动你的 DNA 的转译。这是非常非常有趣。到底我们叫它们维生素，但是其实它们很多时候其实比较像荷尔蒙。Alright, anyway, transcription factors. Okay. So those are just examples, but we need some rules, right? So here are some rules. What factors affect solubility? The cardinal rule of the solubility is like dissolves like. Like dissolves like. You have a lot of OH, going to dissolve in OH. You don't have a lot of OH, you dissolve in not a lot of OH. Assuming the formation of liquid solution takes place in three distinct steps. Step 1, breaking up the solute into individual components. Right? So you have a bunch of vitamin C's bound together, you need to break them apart. Overcoming the intermolecular forces in the solvent to make rooms for the sodium. Right? So vitamin C dissolving water, you also need to move water molecules apart. And finally, you put those individual molecules, vitamin C, into water, right? Allowing the solute and solvent to interact to form the solution. And of course, why do we separate into 3 steps? Because we have 3 different energies, right? So that means now we have the corresponding energy where we define as delta H1. Delta H1 is the breaking apart of the solute. Step 1. Delta H2 is the breaking apart of the solvent. Right? And finally, delta H3 is the combination, and the whole thing we call delta H solution, equals to delta H1, delta H2, delta H3. And you can immediately see, right, delta H1 is going to be positive because you break bonds. Right? You move hydrogen bonds away. Delta H2, the same, you move hydrogen bond away, so both are positive. Only delta H3 is negative, where you're actually forming bonds between solutes and solvents, right? And here's a very cute example. This is called molecular dynamic simulation, 分子动力学模拟. It's to use molecular mechanics based on Newtonian dynamics that basically calculates force and see how things actually change with time. This is a piece of sodium chloride, 就是盐巴哈, dissolving water molecules. This whole thing has a lot of water molecules, but on the left panel, we hide the water molecule, so you only see sodium chloride. On the right panel is the real simulation, and you can see how this actually adds up. How does the bond break in sodium chloride? How does water actually break the bonds? And then how finally they come together? Delta H1, delta H2, and delta H3. Okay? Okay. So we can see that the waters are actually moving. And you can see actually the volume actually is spread out. So it's an MPT, not an MVT simulation. So you see that the waters are moving away. So delta H2, so solvent molecules move away. And you can see that the solvent molecules and slowly some of the ions actually move around single ion. And you can see that some of the water molecules start to surround the this reason because the water molecules start to It's a quantum mechanical simulation method. Not exactly, but And that allows you to actually see the propagation of molecules, atoms in time. Okay? Alright? So what we need to know now is how to calculate, right? So again, we defined delta H solution, the dissolution energy is defined as delta H1, breaking apart of the solute, delta H2 breaking apart of the solvent, delta H3 forming bond between solvent and solute. Okay? So the first one is going to be large and positive because you break bond. Second one is also going to be large and positive because you break bond. Lastly, it's going to be large and negative because you form bond. Okay, now let's take an example that we just saw, right? So we break sodium chloride into corresponding ions. It's gas phase. Why gas phase? Because right now it behaves like a single one, right? Break apart, behave like a single one. Right? This is delta H1, not 786 kilojoule per mole. And then, if you actually added this up, the breaking of the water molecule, and then the solvation of sodium and chloride into the corresponding solvated form, which is a combination of delta H2 and delta H3, we call the energy of hydration. Energy is minus 783 kilojoule per mole. And if you add this up, 1, 2, 3, you get what? You get plus 3 kilojoule per mole, right? And you immediately see something doesn't make sense. So we know sodium chloride dissolved in water, but the energy is positive. 有注意到吗？就是这个能量是正的，但是盐巴会溶于水，所以怎么了？知道？ Alright. The reason is before I come back to this, okay? The reason is note that delta H solution is small but positive. That means that the dissolution requires a small amount of energy. Then why does sodium chloride even dissolve in water? Because later on, as we go to the last topic in this class, we'll learn that it's not delta H that drives the reaction, it's delta G that drives the reaction. That is the Gibbs free energy. And Gibbs free energy is defined as delta H minus T delta S. So for a spontaneous reaction, that means the dissolution of salt in water is spontaneous, delta G need to be negative. And we know delta H is positive, that means this term must be negative. He has a minus sign, right? That means delta S must be positive. And delta S defines the entropy, that means the disorderness. Don't worry about it yet, we'll come back to this. So that means, actually, it is not the the bond formation, bond breaking that drives the spontaneity of the dissolution of salt in water. It is actually the randomness of this hydration that actually makes this possible. Okay? And you can actually quickly look at this reason, right? So, of course, you can think about it in a Born-Haber cycle, where you actually think about it in terms of the latest energy, because you need to break sodium chloride apart, right? So latest energy, of course, this is proportional to charge, individual charges, and inverse proportional to radius. We've gone through this when we talk about ionic compounds. And then you also think about how actually ions actually interact with solvent, right? It's positive and negative ions and hydrogen bond, dipole. So this is going to be ion dipole interaction. So you can see the range is going to be around 40 to 600 kilocalorie. All right, and lastly, you can come out actually with a Born-Haber cycle to think about this. That is, sodium chloride actually breaks into the corresponding gases, which will be this part. So this whole thing will be delta H1. Right? And the remaining thing will just be what? Be corresponding hydration energies. Okay? 这部分有任何问题吗？ Any questions on this part? 应该不太难吧。Please raise your hand if you don't get it. Okay, now I'm going to continue this part. Okay. All right, and polarity effect. Right. So how do we think about this? So a non-polar solvent does not dissolve in large quantity in a polar solvent, of course. And what causes delta G to be positive for disposal of material containing large non-polar induction in polar solvents such as water? Delta H solution is expected to be positive because non-polar molecules don't want to dissolve in polar solvent. Then we expect delta S to be a reason. Right? Again, we need to think about it in both parts. Formation energy, which is delta H, but we also need to think about things getting more random and random. That has the probability, which will come back to delta S when we talk about thermodynamics. Okay? And of course, you can actually look at the tables of different energies don't worry about this yet. We'll come back to that. We'll come back to that when we talk about spontaneity. Okay? All right. And the second effect, the first effect is whether they are polar, right? The second effect is the structural effect. Structural effects. Vitamins can be divided into classes, right? Phase over and water over, as I already told you. And you also need to think about how their structure looks like when they pack together, right? Whether they are actually kind of a long tail structure, or it's going to be what? It's going to be more like spherical. You should have strong interactions. Okay? All right. So vitamin A, composed mostly of carbon and hydrogen atoms, have very similar electronegativity. It's virtually nonpolar. This is considered to be soluble in nonpolar materials such as body fats and largely blah blah blah. And fat soluble vitamin can be built up in fatty tissues, like I mentioned already. Vitamin C is like I mentioned already in this part. Right. So lastly, really just talking about some of the scabies. Okay. Okay. There's nothing much to do. Okay. And last part about solubility, polar effects, structural effects, and last part is the pressure effects. Pressure effects only affect gas. Pressure effects only affect gas. Although pressure has little effect on solubility of solids or liquids, it does have significant effects increase the solubility of gas. For example, carbonated beverage, right? Like Coke, is always bottled at high pressure of CO2 to ensure that the high concentration of carbon dioxide in liquid, and blah blah blah. And the more important part is like this. Right? So what really happens? You want to think about the pressure effects on solubility, something like this, right? So in the headspace, you actually have a lot of gas molecules, which is in equilibrium in the dissolution form. So this part will actually be affected by pressure. And as you pressurize this vessel, you can imagine that the pressure will increase, which will then drive the chemical equilibrium towards dissolution, such that you reduce the pressure on headspace, and again and again. And this can be seen in the next page, where we now have an equation that actually defines how external pressure affects the solubility of particular gas. That is called Henry's law. You need to memorize Henry's law. Okay? So Henry's law states that the amount of gas dissolved in a solution is directly proportional to the pressure of the gas above the solution. That means if you pressurize that gas, more gas will dissolve in the solution, and vice versa. Henry's constant Kh has a unit of molar divided by ATM. Molar divided by ATM. Of course, you can do a conversion on the units. And chi is the concentration of the gas in solution, such that P is the partial pressure of the gas in the gas phase. And Henry's law can be formally written as the partial pressure of that particular gas equals to the Henry's law constant multiplied by chi, which is the concentration of gas in the solution. Okay, 这部分有任何问题吗 ？Okay, now any questions? Now I'm going to tell you something that you need to watch out for, and I think later on we'll talk about it in depth. That is, P is not a total pressure. P is the partial pressure of that gas. Right? So if the pressure of the whole system is say 1 atm, but if you only have 1% of a particular gas, then the pressure here should be 0.01 atm, not 1 atm. And Henry's law constant, of course, you can get it from the table, and you need to watch out for the unit. Right? In this particular table, it's in atm. Okay. And lastly, chi is the concentration of the gas in solution. And now you can actually see that Henry's law constant actually has a trend. That methane is 4.13 times 10 to the second power. CO2 is 1.64 times 10 to the third power. O2 is 4.34 times 10 to the fourth power. CO is 5.71 times 10 to the fourth power. H2 is 7.03 and N2 is 8.52. And what do you see this is the dissolution in water. That is, if the molecule is more polar, like CO, it can form strong interaction with water, hence the Henry's law constant is large, right, to a fourth order. If the molecule is nonpolar like methane, Henry's law constant is small, 10 to the second power. But then you're going to question, N2 is nonpolar, but it's a symmetric molecule, but it has a huge number, 10 to the fourth power. H2 is also a non-symmetric molecule, and it has a huge number. Nonpolar molecule, a huge number. Why? Because these molecules are small. So when you think about gas dissolving in a polar solvent like water, you need to think about two effects. Again, polar and structural. Polar and structural. If it's a polar, it's going to interact with a polar solvent strongly. But you also need to think about it. It's going to actually squeeze in the space made by the solvent, so it also need to be small in the case of dissolution in water. 好，这部分看用中文讲一遍。所以你可以看到分子是 non-polar 的时候，它的 dissolution constant 非常小。那 Henry Stokes constant 非常小。如果分子是 polar 的时候，它的那个就是Henry Stokes constant 很大。所以第一个 polarity effect 很重要，因为我们在 dissolving 一个 polar solvent。但是你会发现，奇怪，都是 non-polar CH4 跟 N2， 为什么 CH4 是10的次方 ，N2 是10的4次方？刚才讲到structural effects， 它必须得要进到这个 solvent 里面，所以它的 size 越小，当然就越容易进去所以 N2 非常小，就很容易卡进去 ；CH4 比较大，就不容易卡进去所以两个 effects polar 跟 structure。Yes。一样吧，一样分吧。对，但是这里我们现在在用的是 contribution of gas。那有些人像我之前上的时候就会被说，那为什么不是用 mole fraction？ 你会发现 mole fraction 跟 contribution 是同一个东西了，乘什么？就是乘它的 molar mass， 对吧？Yeah，let me repeat， 不是乘 molar mass， 对不起，是乘那个 solvent 的 molar mass 再乘上 density。So let me repeat very quickly again. So the question he just asked. So what's chi? Chi is the concentration of gas in solution. Right? Concentration is, for example, gas A. Right? That is the mole number of A divided by what? Divided by liters volume of the solvent. But another chi that we think is this one, right? Which is mole number of A, mole number of A plus mole number of A. And B is your solvent. Agree? And you can see that you can convert mole number to volume. That is MB multiplied by the molecule formula of B is going to give you what? This is mole. This is gram per mole. And you can convert to mass of B. And we need to get volume, then what you multiply by the density. Well, divided by the density. Right? Mass of B divided by density of B. This is gram. This is gram per milliliter when you are going to get the volume of B. So you can see they are the same thing. They are the same thing. And to put this together, and we're assuming NA is smaller than N. Well, volume of NA is smaller. Volume 对，因为我们通常是 solids 嘛，那如果是 liquid 就比较麻烦但是 liquid 是一样这里其实会是整个是 solution， 对吧 ？So he just asked another question. So as you can see, in mole fraction, it's Na plus Mb, but this is the volume of the solvent. Why? Because when we usually do it as a concentration of A, we think about a solid dissolving liquids. And of course, the volume of solids is like so tiny compared to liquids, right? But if it's liquid dissolving in liquids, of course, Na and Mb, the final volume will be, comparable. But of course, then the volume of this is no longer volume of the solvent, right? It's the volume of the solution. Right? So the correct way to say it is the volume solution, which for solid, we usually approximate as the volume of the solvent, right? Because the volume of solid is usually negligible. 这部分有任何问题吗？好，所以基本上用 mole fraction 或者用 concentration 实际上都可以。那你要怎么选择？你要看你的 Henry Stokes constant 是谁。如果你 Henry Stokes constant 是 ATN， 像这个 case 的话，那这个 chi 就应该是 uniless 嘛。那 uniless 就会是 mole fraction。那如果这边是像我上面写的 molar per ATM，molar per ATM， 那这个叫什么 ？molar times ATM divided by molar，ATM divided by molar， 那这个叫什么？这就要是 molar。好 ，Let me repeat in English again. So which one do you choose? Do you choose from mole fraction or do you choose from concentration? Well, look at the Henry Stokes constant. What's the unit? If the unit is ATM, so this is ATM divided by molar, not molar divided by ATM. If it's ATM, this is ATM, this is ATM, that means chi must be uniless. In this case, you're going to use mole fraction because it's mole divided by mole, it's uniless. If the Henry Stokes constant is ATM divided by molar, that means chi must be molar. That means you're going to use this one. OK， 好，这部分有任何问题吗？好，那刚才讲过了，这两个基本上是 invert convertible， 也就是说 Henry Stokes constant 在不同 unit 其实也是 invert convertible。好 ，OK。 And temperature effect on the aqueous solution, as you can imagine, increasing the temperature, gas molecule want to actually drive out of the solution, right? So solubility of several solids as a function of, first is the solids. Of course, solubility increases. The solubility of several solids as a function of temperature. Note that although most substances becomes more soluble in water with increasing temperature, sodium sulfate and cerium sulfate becomes less soluble. So for solids to dissolve in solution, increase the temperature, the solubility increases, right? As you can see, this is sugar, this is sodium, potassium nitrate, sodium nitrate, etc. Why? Because remember, delta G equals to delta H minus T delta S. And by increasing temperature, of course, you make the minus T delta S turn larger. Of course, delta G becomes more negative, right? Because temperature increase, negative temperature becomes more negative, right? So this. 这部分有任何问题吗? Okay. But it's not the same for gas. Right, so this is something to watch out for. If the question say increasing temperature will increase solubility of all substances in a given solvent, then the answer will be no, that's not true. Why? Because that is almost always true for solids, but that is going to be false for gas. The solubilities of several gases in water is a function of temperature at a constant pressure of 1 atm of gas above the solution. As you can see, methane decreases, oxygen decreases, carbon dioxide decreases, nitrogen decreases, helium kind of stay the same. And why? Again, this is due to delta S, right? So delta S is a driving factor. Now you can imagine having gas molecule dissolving solution and having gas molecule as a gas. Of course, as a gas, the randomness is going to be more, right? Because it's freely moving in the headspace. So that means the direction to increase delta S is actually becoming gas. Increasing temperature, of course, will increase the contribution of entropy. Hence, you really want to become gas, right? So you will actually becomes gas forming will actually occur if you increase temperature. Okay, and this is one very important thing that causes a lot of issues in our daily life. This is actually the effect of temperature. The decreasing water solubility of gas with increased temperature is also responsible for the formation of boiling scale. 这就是水质。The bicarbonate ion is formed when carbon dioxide dissolves in water, causing the carbonate ion. So any carbon dioxide, like in the atmosphere now, will actually dissolve in water to form bicarbonate. Bicarbonate CO3 2 minus with a proton, so H3O3 minus. Hence the carbonate is this, and bicarbonate is with a proton. All right. When the water also contains calcium 2 plus soluble in water. Well, but calcium carbonate is insoluble. When the water is heated, right, it forms carbon dioxide. What will happen? This will disappear into the headspace because increasing temperature decreases the solubility of gas. This chemical equilibrium will then shift back to create more carbonate. And then carbonate finally will actually form, which is not shown in the equation here, formed insoluble salt with calcium 2 plus. Carbonate and calcium 2 plus becomes insoluble, which becomes a boil scale. And this is indeed what you see inside your pots. Right? 在你的水壶里面为什么看到这些，就是因为这个原因。因为加热的时候，水中的 bicarbonate 里面的 CO2 大量的跑到空气中，所以它从 bicarbonate 变为 carbonate， 即便 pH 7的情况下是不允许的。Carbonate 就会跟你的水中的 calcium， 我们的calcium 形成这些水质，就是我们所谓的石灰calcium. Okay? Alright. Any questions on that part? We'll kind of finish the whole factors affecting solubility. 这部分有任何问题吗？好，这部分应该不算难哦。Please raise your hand if you have any questions. Otherwise, I'm going to move on to the next section. Alright? So next section is vapor pressure and change of states. So vapor pressure is something defined as this. Behavior of a liquid in a closed container. So make sure the first keyword is a closed container. If you have a liquid inside a closed container, as time passes, what will happen is the liquid will actually evaporate into the headspace, right? And this is what we call vapor pressure, and we previously defined it already for liquids and solids, right? When we talk about phase diagram, right? So initially, net vapor evaporation occurs as molecules are transferred from liquid to a vapor phase, right? Because initially we didn't have any vapor in the headspace. As the number of vapor molecules increases, the rate of return of liquids increases until the final rate of condensation equals the rate of evaporation. That is when we reach chemical equilibrium. And this is defined as the vapor pressure. And you've seen this, right? So just a recap. vapor pressure can be measured by using a nanometer like this, right? Just fill with mercury and with some of the liquids you try to measure, and you see how the height change, right? And at the 1 atm, it's going to be 760, and with different vapor pressure, this number will change, right? And of course, you've seen this plot before, and we're going to spend a little bit more time later on. This is what? This is the Van Hoff's equation, where you actually plot the natural log of P vaporization against 1 over T. You can actually get a negative line. And the slope is what? The slope is minus delta H naught divided by R. Heat of vaporization divided by ideal gas constant. And the offset is what? The Y offset at this point is delta S naught divided by R. That is the entropy of vaporization divided by ideal gas constant. And which is a quick reminder, right? So please remember this equation, Van Hoff's equation, definitely will occur again for solubility. Right, so it's going to be plotting natural log K over 1 over T, and this will be a slope, this will be the y-intercept. And it's a reminder of Van Hoff's equation. All right, and the presence of a non-volatile solute lowers the vapor pressure. Why do we come back to this? Because right now we don't have a pure liquid. We have a mixture of a liquid. How does this actually affect the vapor pressure? Say we have water, and we just keep adding ethanol to it. How does that change our vapor pressure? Okay. So as you can see in this picture, if originally this liquid G, has a vapor pressure of 3, if we add another liquid yellow, liquid Y, which is not volatile, the vapor pressure will drop to 2. So this is the original observation. When we mix two liquids to form a solution, the vapor pressure will change. Okay? And a very limiting example of that will be, what if we have a liquid nothing, right? Liquid nothing. Then you can imagine that everything will just transfer to one side. And the other thing, what will happen is, what if you just add some salt in here, right? Then of course this liquid becomes less volatile because of the ion dipole interaction, and liquid will migrate to the other side. 好，中文快速讲一遍。如果你有一杯纯水跟另外一杯盐水，那盐当然会增加什么？盐当然是不是 volatile 嘛，对不对？所以盐水的 volatility 会比较低，纯水的 volatility 比较高，所以这时候会发生什么事情？这时候发现这边它的 vapor pressure 比较低，这边 vapor pressure 比较高，而 pressure 会从高的往低的走，对不对？所以你就会发现水一直转移到里面。为什么？因为 vapor pressure 这边低 ，vapor pressure 这边高，最后你就会发现什么？你的 beaker 竟然在没有任何作用的情况下干掉，然后另外一边的水量增加。Let me repeat it in English real quick. You can imagine you can have a pure water and you can have a solution, say table salt dissolved in water. Of course, table salt is not volatile, it's solid. So you can imagine that the vapor pressure of the salt water is going to be lower than the vapor pressure of water. And of course, vapor go from high pressure to low pressure. So you can imagine that water will just move from one beaker to the other beaker. Until what? Until one of the beaker gets empty, the pure water, and the other one gets saturated. And nothing really happened, right? It's just pure vapor pressure. Now one has lower vapor pressure and the other one has higher vapor pressure. Alright? And this is the part where we're going to learn how do we quantitatively solve this. 那数学上来说，我们到底要怎么做？那这个叫做 Lot's law. So this is actually later on coined by Lotz. So Lot's law says how much of the ion how much ion is enough to achieve the complete transfer. This is governed by Lot's law that relates the mole fraction. Again, you see mole fraction again, because it really talks about how molecules interact with each other, right? Of the solvent to its vapor pressure. That is chi of the solvent multiplied by the vapor pressure of the solvent by itself equals to the vapor pressure of the solution. So for example, if you have water, which is the vapor pressure of 28 at 1 atm, and if you only have 50% of water in this solution, then the final vapor pressure of the solvent is going to be 50% of that will be 14 torr. 好，这部分有听懂哦。So you can see that you can actually draw a straight line when you actually have ion inside a volatile liquid. Where the mole fraction of the solvent, if it's 0, then of course the vapor pressure of the solvent will be 0, right? That means you just have table salt. As you drop in more water into the solution, into table salt, it increases the mole fraction of water in this table salt solution from 0 to 1. Of course, the vapor pressure of the solution will gradually increase to that of the vapor pressure of pure water, which is 23, 25, or 28 total. Right, that's the removal of all the salts. And this is a linear line, and we call this lossless law. Okay. And of course, if it's a liquid instead of a liquid solid, then the other liquid also has vapor pressure. Then how do you calculate total vapor pressure? It's just going to be a sum of the partial pressure, right? For liquid solutions where both components are volatile, a modified form of lossless law applies. That is, the pressure of the total vapor pressure equals to partial pressure of A plus partial pressure of B if this is a two component, which if each of them is going to follow lossless law, right? Each one is going to be the mole fraction of A multiplied by the pure vapor pressure of A. So then you can write mole fraction of A multiplied by the vapor pressure of A when it's pure, plus mole fraction of B multiplied by the vapor pressure of B when it's pure. So lastly, we can then come up with a final diagram like this. This is the modified lossless law when you have a liquid mixture. That is, when the mole fraction of B increases when you go from the right to the left, then you're going to see that finally this term will just be 0, right? Because mole fraction of A is 0, mole fraction of B will be 1. Of course, the final pressure is going to be that of the pure B. And then go to the other side where the mole fraction of B decreases while mole fraction of A increases until it hits 1. That means chi A is 1, chi B is 0, and everything is going to be pure vapor pressure of A, PA naught. In the middle, you're going to have a straight interpolation from chi A naught to PB naught to PA naught. And of course, the corresponding components of partial pressure B and partial pressure A, which then add up to give you the green line. 这不会有任何问题吗？好。And of course, if the world is that simple, right? So of course, we make some model systems and we think this is going to work. Where the total pressure is simply the sum of partial pressure A and partial pressure B. But in reality, a lot of times it's not true. Right, so there are two cases for something called the non-ideal solutions. And you do need to memorize these two. One is positive deviation. As you can see, this is the theoretical from ideal lossless law solution, and you increase. The other one is negative deviation from lossless law, where this is the ideal and it decreases. Right. So A, the solution of which P total is larger than the value calculated by lossless law would be this case. It's B, sorry. And C, a solution for which P total is smaller than the value calculated by lossless law in this case. And why? The reason is this. Right? So for negative deviation cases, you can think about this as an example where you mix chloroform, where methane has its 3 hydrogens replaced by chlorine. So it's a very common use organic solvent. It's mixed with acetone, another common use organic solvent, where you have 3 carbons and 1 carbon in your group. Okay? Now to make the negative heat of solution indicate, so again a keyword, if the heat of solution, if you mix A and B together, delta H1 plus delta H2 plus delta H3 is very negative. That is, you have a very negative heat of solution, indicate especially strong solid-solid interaction, and such that solutions are expected to show negative deviation. So direct correlation. If you have negative heat of solution, then you're going to see negative deviation from lossless law. That means both components have a lower escaping tendency in the solution than the pure liquids. And this behavior is demonstrated here. Why? Because you can imagine if just by chloroform itself, what will be the interaction? Dipole, right? Chloroform has very electronegative atoms, so it's going to be partially negative this side, partially positive this side. So another chloroform molecule will just type partial negative, partial negative, positive, partial negative, partial positive type dipole. It's going to be the same for acetone. Partially negative, partially positive, right? So individual pure liquids only have dipole-dipole interactions, but if you mix them together, what you see hydrogen bondings, right? Because this hydrogen is very partially positive, this oxygen is very partially negative, then they can actually form hydrogen bonding. And of course, from the table we already saw before, this one, hydrogen bondings has interaction energy about 10 to 40 kcal per mole, while dipole only have 5 to 25 kilocalorie per mole. So of course, forming hydrogen bond will give you stronger bonding, which then releases energy. While breaking weak dipole interaction, you only need to waste small amount of energies, right? So this is the case where when they are individually, they form very weaker interactions. When they are mixed together, they form stronger interactions. Okay, and this will give you what? This will give you a negative heat of solution. This will give you a large negative heat of solution, which then will correspond to a negative deviations from Gauss's law. All right, and of course, that means the other one will be true, where if the individual have stronger interactions and mix them, they form weaker interaction, will give you positive. And one very good case will be mixing ethanol with hexanol. If two liquids mix endothermically, that means they have a large positive heat of solution. This indicates that the solvent interactions are weaker than the interactions among the molecules in the pure liquids. More energy is required to expand the liquids than is released when the liquids are mixed together, right? Delta H1, delta H2 are large, delta H3 is small. In this case, the molecules in the solid solutions have a higher tendency to escape than expected, right? They don't want to stay in the solution, hence you see a positive deviation. And you can understand this, right? Because when ethanol and ethanol mix together, they form hydrogen bondings. Hexane mix together, you form London interactions, right? Dispersive interactions, non-polar interactions, right? Because these are non-polar bonds. But if you mix hexane and ethanol together, you can see that hexane can only interact with the backbone of ethanol. And because hexane is really big, what will happen? Hexane will actually block the OH group such that the other ethanol cannot actually interact with this OH group. Okay, we mentioned that hexane will actually cover this whole ethanol molecule.